We continue the same exercise. We are in exercise, I think, 12. So we did up to E. So now F. So V Banach, T in LV, compact, M as above. Okay. Then T of NM is in NM and T of FM is in FM. Okay. So X is in NM. So I minus T M X equal to 0. So T of I minus T M X equal to 0, which implies that I minus T M of Tx is 0 because T commutes, and therefore this implies that Tx belongs to NM. Okay, so that proves the first one. Similarly, X is in FM, X equals I minus T M times Y for some Y. So Tx equals I minus T M T times that Y, which is equal to I minus T M Ty, and therefore which belongs to Fm again. Okay, so that now G I minus T therefore maps Fm to Fm is an isomorphism. So I minus T is continuous, T is compact, okay, because we are in a closed subspace, nothing has changed, and therefore let us assume, so X belongs to Fm means X equals I minus Tm times Y for some Y. Okay, so I minus Tx equal to 0 implies that I minus T M plus 1 Y equal to 0. So that means Y belongs to Nm plus 1, which is the same as Nm. So I minus Tm Y equal to 0 implies X equal to 0. Okay, so I minus T is 1 1 T compact, so this implies on 2, and by the open mapping theorem this implies it is an isomorphism. Okay, so remark, all the above results in exercise 12 are valid when we consider lambda I minus T, where lambda not equal to 0 is an eigenvalue of T, compact of course, because you can write this as lambda times I minus T by lambda, and therefore all the results which we wrote before, they are all true. So we have then that the dimension, so M as above, then dimension of n of I minus, so lambda I minus T power M is called the algebraic multiplicity of lambda, and dimension of lambda I minus T we know is called the geometric multiplicity. It's the number of independent eigenvectors. So you have that geometric multiplicity is always less than or equal to the algebraic multiplicity. So the number of eigenvalues, because it's an increasing space, and therefore the dimension is always larger. So you have this. If T is self-adjoint, compact, this implies that M equals 1, therefore algebraic multiplicity is the same as the geometric multiplicity. And null space of lambda I minus T power M is called the generalized eigenspace of lambda. Okay. So now let us continue. So 12, now we are in 13. So V Banach T in LV compact, lambda eigenvalue of T not equal to 0. Lambda not equal to 0. Okay. So then we put M, let M be as above, and we set, define or denote null space of I minus T power M, sorry, lambda I minus T power M as n of lambda, and range of lambda I minus T power M as f of lambda. So then we know that V is equal to n lambda direct sum f lambda. If lambda not equal to mu are distinct non-zero eigenvalues of T, show that A, mu I minus T is an isomorphism n lambda to n lambda. So solution, T of n lambda we saw was in n lambda, we saw that already, and therefore this implies mu I minus T also maps n lambda into n lambda. Okay. And if mu I minus T of x equal to 0, this implies that Tx equal to mu x. So lambda I minus T of x equals lambda minus mu of x. Okay. And we know that 0, x belongs to n lambda, okay, and therefore 0 equals lambda I minus T power m x, which is equal to lambda minus mu m x, and lambda is not equal to mu, and therefore this implies that x equal to 0. Okay, so mu I minus T is 1 1 T compact, and this implies on 2 and implies it's an isomorphism. B, show that n mu is contained in f of lambda. So solution, let x belong to n mu. Then we know that V is equal to f lambda direct sum n lambda, and therefore x can be written as y plus z, y in n lambda. So let me n lambda direct sum f lambda, it does not matter, but it is better to z belongs to f lambda. Then for k large, you have that mu I minus t power k y, sorry, x equal to 0. There is some k, we know, because that is a number corresponding to the algebraic multiplicity of mu. Okay, okay, but mu I minus t power k of x of y continues to live in n lambda, and mu I minus t power k of z continues to live in f lambda, and you have mu I 0 equals mu I minus t k x, which is equal to mu I minus t power k y plus mu I minus t power k z. But then this decomposition has to be unique because it's a direct sum. So this implies that mu I minus t power k y equal to 0, and mu I minus t k z is also 0. And since mu I minus t is an isomorphism on n lambda, and therefore you have that y equal to 0. So this implies x equals z, which belongs to f lambda. So we have that n mu is contained in f lambda. Okay, with this I will wind up the exercises for this chapter, and also this course has come to an end. I do hope you enjoyed the course and you found it a useful learning experience. All the best.